Hello everyone, welcome to 1045 Engineering. We are here with yet another video in our Mastering Data Structures and Algorithms in Java. And today's topic is binary search. Let's start. Okay, so by definition, binary search is a highly efficient algorithm used to search for a target element in a sorted array. Unlike linear search, which checks each element sequentially, binary search works by dividing the array in half and eliminating half of the search space with each step, and thus drastically reducing the number of comparisons. How does it reduce the number of comparisons? Because rather than checking for each element, it divides the array into half and then searches either on the left half or on the right half based on the logic. Key concept is, so one of the basic requirement for binary search is that the array has to be already sorted, array or the list. So linear search you can perform on unsorted arrays, but binary search you can perform only on the sorted arrays. Only then we can perform the left half, right half of the binary search. Okay, so just to provide you with an example, let's say we have 1 2 3 4 5 6 7 8 9. Okay, and since it's a searching algorithm, we have to find a target, right? So let's say our target is 7. Okay, so we'll find the mid element, we'll see 5, we'll check. We already know at 5, right, that it is in the upper half, right? We can see 7 here. It wouldn't make much sense, since the algorithm already sorted, to start from here. You pick any element, let's say randomly from 1 2 3 4 5 6, you are supposed to find out 5. Okay, and randomly you come at 4. You already know, since it's sorted, that 5 must be in this side, right? But then you would not start searching one after the other, 5 then 6 then 7 and then find 7, right? So we'll use the binary search logic. So we'll come back to this part. Okay, so let's see how binary search works. Okay, so we'll remove few of the things. Oops. Okay, we don't need this. Okay, let's say the initial array is 5 6 7 8 9. This is our input array, or you can call list. Okay, yeah, so it says start with the entire array. Okay, we are starting with the entire array. Calculate the middle index of the array. Okay, so we'll find the middle index. So from indexing perspective, it is 0 1 2 3 4 5 6 7 8, right? So we would have to find the middle index. There are multiple formulas that you can use. Easiest one is that you simply do left plus right minus left by 2. Okay, to calculate mid, let's say. Okay, so 1 2 3 4 5, 4 element this is 1 2 3 4, 4 element this is. We know that this is our middle element, right? Okay, calculate the middle index of the array. So we found the middle index of the array as 4, right? As per the formula, it will go 0 plus right, that is 8. 8 minus 0 divided by 2, it will be 0 plus 4 equals 4. Okay, so we have our middle index as 4 here. Compare the middle element with the target. Okay, let's take a target. So let's say the target, let's select a complicated target. Let's say target is equal to 8. Okay, so we have to find out whether 8 exists in this list or not. Okay, since we already know it is sorted, we picked up the element, the mid index, that is 4. So the middle element that we got is 5. Okay, this is index. Okay, now let's see, compare the middle element with the target. So we compare 5 with 8. 5 is not equal to 8, so we know that this is not the answer. So if the middle element matches the target, return the index. Okay, so if it matches, we'll return 4, but it does not match. If the middle element is greater than the target, repeat the process on the left half of the array. Okay, so middle element is not greater than, right? If the middle element is smaller than the target, repeat the process on the right of the array. Okay, so the middle element, that is 5, is actually less than the target, which is 8. So we'll start our next journey on the right hand side. Okay, let's say we'll start our next journey on the right hand side. So 1 2 3 4 5 6 7 8 9. Binary search is a really easy algorithm and very efficient in terms of time complexity. Okay, so it's very good that we understand this algorithm. So we check the middle element. It's not same as the target. This is our target, and we know that the middle element is smaller than the target, so we search in the right half. But we don't do linear search here, we do the binary search again. So now consider this as one array. Okay, though it could happen you can start with 6 also, but doesn't matter much. You can start with 5, or let's say we want to search in the second half, so we start with 6, right? So now in this we have to search. So this will be our starting index, this will be our ending index. So the midpoint will come out 0 4 by 2 2 0 1 2. Our middle element would be, in this case, 0 1 2 5 plus 8 minus 5 by 2. So that would be 5 plus 3 by 2. So 3 by 2 in this case would be 1, it will be 6. So this will be our next mid element, right? Now we take out 7 and we compare it with 8. So 7 is not equal to 8 and 7 is less than 8. If 7 was bigger than 8, we'll search in the left half, that would be 6. But 7 is bigger than less than 8, so now we know that we have to search in the right half. And in right half only 2 elements are left, 8 and 9. And in next comparison we'll get the mid element as the first element. Since 0 plus 1 divided by 2, it will be 0 only. Okay, so we'll get this as the next mid element, and now we'll compare 8 is equal to 8. That is our target, right? Now if you notice, we didn't compare 1, we didn't compare 2 3 4, we didn't compare for 6, we didn't compare for 9. Only in 3 chances we reached our target element. A similar case could have happened. Let's say our target is 3. Okay, so we go with the same approach. We have the complete array which is already sorted. We find the mid element comes here, 5. We compare 5 with the target. So 5 is bigger than the target. We already know our element is going to be in the first half. We find the midpoint, we get it to 2. Now we compare 2 with the target. Target is 3, 2 is smaller than 3. So we know that the solution exists in the right hand side half. Now we take 3 and 4, we again do the binary search, and we again find the midpoint as 3, and we compare it with 3, we find the target. But what happens if you have a target, let's say I have a target 3.5. okay, so when I compare it with 3, it's not the solution. So last point is 4th, I check it with 4. 4 also does not match the target, but I know that all the numbers on this side are bigger than 4, all the numbers on this side are smaller than 3. So the target does not exist, so I should return -1, that we did not find the solution here, right? So it can happen that the target that you are searching for is not there in the list. But for that also you do not have to compare all the elements, you will directly know it with the algorithm, and you have to make a breaking point here. Okay, let's go back. Then continue dividing the array in half until the target is found or the search space is exhausted, like we already discussed. Okay, let's try to code this. Okay, so we need a search method. Okay, yeah, as of now you are aware what all do we need. Let's see. Okay, let's see what all do we need in this for this algorithm to work. We need few things. One is we need the array, that would be 1. We need midpoint, that is second thing. Third is we have to do this recursively, right? So we have to do it on first we have to do it with one midpoint. We did the binary search on the whole, we found it's in the second half, so we again have to perform binary search on the leftover half. Similarly, then we have to perform binary search in the leftover half, then leftover half, and then leftover half, right? So we have to make recursive calls. Now we can use a recursive method that calls binary search again and again, or we could go with the iterative approach to implement the same. Okay, we'll use the iterative approach. So let's see. We'll say main method to perform binary search. Okay, I'll say public static int binary search. So what do we need from here? Array, int array, and our target, int target. Okay, now we need two indexes, because here we are doing our calculations also on the, so the formula that we are using is left plus right minus left by 2. That will give us the midpoint, right? So we need pointers for left and right. So we'll say int left is equal to 0, int right is equal to array dot length minus 1. Okay, now since we are using the iterative approach, okay, so we need a loop that makes sure that we have to run through this as long as the left is smaller than the right. So while, like in this case, right, when we are searching in the end between 3 and 4 here, when we were discussing that the target is 3.5, our left would already be at 3, our right would already be at 4, right? We searched through 3 and we did not find the solution. We went to 4, we updated our left pointer. Now left pointer has reached the right pointer. That means after 4 we cannot make any further searches, because then left pointer would be bigger than right pointer. So that is our break condition. Okay, so we'll use the same if while left is less than equal to right, and now we'll perform. First let's calculate the midpoint. Int mid is equal to left plus right minus left by 2. Okay, now we'll check if we have already found the target on the midpoint. So check if the target is present at mid. Okay, so we'll directly compare. If array of mid is equal to target, that means we found the solution. So let's return the index. So we'll say return mid. But let's say we do not find the index, so we'll use the other two conditions. So if target is greater, ignore the left half. So we'll say if array of mid is less than target, that means our solution is in the right half, so we'll update our left pointer. So left pointer will become mid plus 1, right? Why mid plus 1? Because in the first comparison we already compared 5, right, which was our midpoint, so we don't have to take it again. So we'll start from 6. So we updated our left pointer to arrive directly at 6, so that is mid plus 1. Right would remain the same. On the other hand, if we would have gone to the left half, we would have updated our right pointer, and that would have been mid minus 1. Okay, let's go. So and if target is smaller, ignore the right half. Okay, so we'll say if array of mid is less than target, right is equal to mid minus 1. Okay, that's all. Now once this complete while loop ends and left is equal to right, and in the next comparison left is bigger than right, and the while loop breaks, and that would mean that we did not find a solution. So we should return minus 1. So we'll say return minus 1 target not found. Okay, let's go here. So we searched for the left half, we searched for the right half, and we did not find our target, like in the case for 3.4. so we return -1. Okay, now let's create the main code and run the system. Int array is equal to 1 2 2 3 4 5 6 7 8 9. Okay, now int target, let's give it 3. Let's give the easy one 5, that would directly be at the midpoint, right? And we'll change the targets again. Int result is equal to, we'll call binary search, pass the array, pass the target. Now if result is not equal to -1, that means we have found our target. So we'll say system.out.println element found at index, and then we'll return result. Okay, else that means the index has not been found. We'll say system.out.println element not found in the array. Okay, let's run this. Element found at index 4, 5 0 1 2 3 4 at 4th index. Okay, let's change it 3. What happened? It didn't run for some reason. Let's run it again. Oh, I guessing there's some issue or something. What's the issue here? Not sure why is it not printing the result. Target is equal to 3, it should get found. Let's see for 8. Element not found in the array. 8 is directly here. What did I miss? There is something I'm missing here. 8 is defined target. Let's see, let's quickly check this. Okay, so we call binary search. We define the left, that is 0. We define the right, that would be array of length -1. So it gets the value 8, it gets the value 0. Okay, if left is less than equal to right, we'll continue to perform this. Mid would be left plus right minus left whole divided by 2. That is also correct. Why there is an underline on this? Reassigned local variable. Oh, okay. Sorry, my bad guys, my bad. These values, no, these values should be outside only. This is the starting point. Reassigned local value, left 0. Reassigned local value, right. There's no issue in that. Okay, int mid would be left plus right minus left by 2. Array of mid is equal to target, we return mid. If array of mid is less than target, we make left is equal to mid plus 1. If target is smaller, we ignore and we say right is equal to mid -1, and otherwise return -1. Element not found in the array is getting printed. Why? So it's not coming for 8. Target is greater, right? So let's see if the call is coming here or not. Start on println we are here. Let's see. Okay, so it did print we are here. That means then it updated, left became mid plus 1. Left is still less than or equal to right because right has not been updated. So that is correct. It should come again. Mid would become left. That would be let's print the values of mid. I'm sorry that something is breaking and I would have to find it out. Let's do it. Okay, we need to find out how many times the code is running and actually if it is running or not. So mid was 4 in the beginning, and we came to here also, we are here. Left was reassigned. Oh, what's wrong here actually? Oh, my bad. This is actually not good. So I'm doing the if, and after the if I am doing the if again. It is supposed to be else. Sorry. Let's remove command X. Okay, and then I don't need this condition. Okay, let's run now. It should work now. There was a small typo error, index founded error 7. Okay, we don't need this and we don't need this. Let's run it again. Good that we tried with different examples. So element found at index 7, and if I now try for 3.5, what's the issue? It's integer. Let's say I try for, I'll remove 3 from here directly. Okay, and I search for 3, element not found. Okay, so we are good. And I'll make it 7. Okay, so this is how the algorithm works. Okay, so we define the left, the right, then we follow the iterative approach from left to right, and we calculate the midpoint. Each time we check if element is at the midpoint, then we return the index. Otherwise, if the target is greater, we increase the left to mid plus 1. If the target is smaller, we reduce the right by mid minus 1. Okay, let's go next. So in summary, time complexity of binary search, of course, you can guess it's log of n. It's a logarithmic solution because in each iteration we reduces the array by half, and we do not have to go through all the elements. Space complexity is 1 because we do not require any extra space. Some of the pros: it is more efficient than linear search for large data sets. Yes, correct, because let's say there are 1 million data sets. We would have to make the search a very less number of times in the log n manner, but in a linear search we would have to search through entire list of 1 million elements. Okay, time complexity of log n, which is superior to linear search O of n for large arrays. I think these both points are same. Cons: it only works on sorted arrays, so yes, that is one of the drawbacks. You always need the array or the list to be sorted to perform binary search. Also, it is slightly more complex than linear search because yes, for linear search we directly search the element one after the other. We just use a for loop. We do a comparison with all the elements, right? So that's all from today's video, everyone. If you guys have any comments, please let me know in the comment section. In the end, please like, share and subscribe. Thank you.